Welcome to Look No Hands, the remote interactionless attack surface of the iPhone. You're in Lagoon GHI, and the speaker is Natalie Silvanovich. Before we begin, though, we have a few brief notes. Please stop by the business hall located in Mandalay Bay, Oceanside, and Shoreline Ballrooms on level 2 during the day, and for the welcome reception at 5:30 this evening. The Black Hat Arsenal is in the business hall on level 2. And join us for the Pony Awards in Lagoon JKL at 6:30. The wrap room for this talk will be in Reef A, which is down the hall. And please put your phone on vibrate or silent. Without further ado, Natalie.
Hi, everyone. Thanks so much for coming. Today I'm going to talk about the remote interactionless attack surface of the iPhone. I'm Natalie Silvanovich, and I'm a member of Project Zero at Google. And iPhone remotes are something we've been thinking about for a long time. A while ago, there was this tweet from Chowkey that said, "Rumor says that from a zero-day exploit perspective, the security of iMessage is less than these other messengers." And if you don't know Chowkey, he runs Zerodium, which is a company that pays for all sorts of exploits, including iPhone exploits. And this says that they'll pay $500,000 for an iMessage remote and $1.5 million for a zero-click remote jailbreak on an iPhone. Also, there was this article about the UAE secret hacking team and their tool called Karma. And some excerpts here are that it did not require a target to click, and it relied on an undisclosed vulnerability in iMessage. So there's been these little glimmers of the fact that attackers are using this type of vulnerability. But then when you look at public research, there's not so much information. And there's even people that doubt that these types of bugs exist. So I wanted to get to the bottom of this and find out whether these bugs exist, and if so, where are they in the system, and how do they work? Also, I wondered, was it just iMessage, or are there other remote attack surfaces too? And I wondered if these bugs are exploitable. So to start off, what do I mean by an interactionless bug, or a zero-click or fully remote bug? Well, it means that there is absolutely no user interaction required. You can just sit a device somewhere and run your bug or exploit, and it will compromise that device. Also, I would say a short wait time is a good requirement too, just because people will be like, oh, someone will eventually unlock their phone, someone will eventually open the browser, but that's not really what we're looking for here. We're looking for the ones that require no click and work fast. And also, they need to require a reasonable set of identifiers, usually a person's email address or their phone number. Once you get into things like IP address or IMEI, you need to also find a way to get that identifier, or it's harder for an attacker to target someone. So, thinking about this is the remote attack surface of the iPhone that I looked at. There is SMS, which is text messages, and then there's all these special SMSs that your carrier can send. For example, there is Supple, which sends GPS ephemeris data. And then there is MMS, which is basically SMS if you have a media attachment. And then there is iMessage, which is the messaging client on the iPhone that uses Apple's server for messages. And there's regular messages, and then there's extensions. Have you ever seen the thing on the iPhone where you point the camera at your face, and there's a giraffe, and you move your mouth, and the giraffe talks like your mouth? That's an iMessage extension, and that's also part of the attack surface. And then there are things that you can do over the public internet. There's the email client. If someone sends you an email, sometimes it'll be processed even if you don't open it yet. And then there's also a packet processing on the public internet, though you need an IP address for that first, usually. So I started off by looking at SMS and MMS, and in hindsight, this was the wrong call. I had this idea that everyone talks about iMessage so much, no one must look for bugs in the other places, and there'd be lots of bugs in them. That was wrong. This was actually a fairly difficult attack surface. So I looked at the comm center binary, which on the iPhone is where SMSs are processed. And I'm going to flip through these quickly, but this is the message flow. This is more for people if they want to look at this at home. These were generally the methods that get executed when you get a raw SMS. And this is a similar diagram for MMS. So the first thing I did was I wrote applications that exported some of these symbols and then fuzzed them just sending random data. That didn't work. And then I noticed that the SMS on the iPhone actually has a built-in SMS emulator. And it's incomplete. It requires a library, which I assume is on Apple internal devices, but I didn't have. So I reconstructed this library. I basically made up a library that on a jailbroken iPhone will call the right functions, and it would basically allow you to simulate a deliver PDU being sent to your device. And I put this on GitHub today, so if you go to this location, you can get a lot of tools, including this SMS simulator. And I used this for fuzzing, but unfortunately, that didn't really work out either, and I didn't find any bugs in SMS. But then I started looking at those special SMSs that your carrier can send. And one thing that I noticed was visual voicemail. And visual voicemail is when you use your mobile device, you'll have an email-like format for your voicemail messages. So you'll see the number, and then you'll see the play button and the message, and sometimes a transcript. And the way this actually works is that your carrier will send you an SMS, and that will have an IMAP server location in it. Then it will ping that IMAP server and pull down all your messages. And this seemed okay if it was just the carrier that could do this, but I tried sending the messages, and you could send this from any SMS device. You know, I could send it from the SIM card I bought at the gas station. So I looked at this message a little bit more, and here's an example of it. So I, for example, would replace vvm.att.com with, natashenka.com, and then it would just ping my IMAP server. And I thought this would actually be a pretty good attack surface. Here's why. On iOS devices, they use the same library for VVM as they do for regular IMAP and email. And that's kind of a change of attack surface. When you think about IMAP for email, really it's the server that's the attack surface. Since the beginning of IMAP, people have tried to compromise servers to read everyone's emails. But the idea of a client being attacked by a malicious server, that's not really an attack surface in email, because you only use servers you trust, and it's a lot less common for a user to put a new server in. But visual voicemail changes this attack surface. It means now that anyone from a remote context can make you ping an IMAP server for messages. So I wondered if the people who wrote the library had thought about this context switch and hardened that surface. So I took a look at it. And there's some limitations here. One is that your carrier has to support it. And I put some asterisks on that, in that I think there's probably ways to get around this, especially if you have a base station, but no guarantees. Also, some carriers will filter this. They'll have, for example, firewalls on their network that prevent you from hitting the server. But there were still lots of SIM cards I tried this with where that was not the case. And finally, your user has to have used email or voicemail exactly once. They have to have recorded a greeting, or else this doesn't work. So I reviewed the IMAP server in IDA, and I didn't find any bugs that way. So I wrote a fuzzer that generated malformed IMAP. And then I had this SMS simulator that I'd written already, so I was able to just make that ping my device over and over and over, and then it would ping my IMAP server over and over and over, and then get all the fuzzed input back. And doing this, I found one vulnerability. I found this use after free in IMAP namespace processing. And the way this works is there's a command in IMAP called list, and this will get the separator for the IMAP server, which is typically a slash or a backslash, but it could be anything. And then it will try and get the prefix, which is sometimes necessary to access a path, calling this command called namespace. And what happens is it will call list, and then it will cache the separator, and then it will call namespace, and if namespace fails, it will free the separator in the connection. But then it doesn't check the return value of this call. So what ends up happening is that it will continue to use this cached value even though it's been freed. So this is a use after free. It lets you call a selector on a freed NS object, but it was also kind of a limited info leak in that what the system actually does with this separator is it will save it for later, and then when it tries to get a mailbox, it will actually append it. So sometimes when I use this bug, I would get, a pointer back or some data back, but it was like super unreliable. Like I could get it to like 3 out of 1,000 times tops, and it would lock the process otherwise, and I would have to restart it. So I never got this reliable enough to be able to do anything really useful with it, but it did seem like an interesting bug. So then I started looking at the email client. So what happened here is that looking at this IMAP server, I did find some parts that were only accessible via email. For example, it would only process certain MIME types. So I wondered if I could hit some of this code just by sending an email. So I tested this with the native email client on the iPhone. I'll admit I'm not clear on how realistic this setup is. There's kind of two concerns. One is that email addresses or email providers sometimes use third-party clients. The other is that email providers sometimes filter content. So I think it would be hard to come up with a universal bug in mail because you have to worry about every email provider filtering it. But I did my testing with Gmail set up on the native client, and anyhow, I found one bug that worked. Found this one by code review as well, and it turned out to be fixed already. Basically, it looked like it was exploitable but difficult to exploit in 11.3, and by 12, the functionality had been removed, so it wasn't there anymore. And it is probably the strangest bug I have ever seen. It was very, very unusual. So basically, in email, you have a MIME type, which is the type of the message. So it's like your text or your HTML or your JPEG. And the way it processes the MIME type is that it will take the MIME type as a string and append a code to it, and then call that method. And that works, except there are other methods that start with decode. So you could call all these other methods, and some of them had different numbers of parameters or unexpected functionality or that sort of thing. So once again, this led to a crash in 11.3, but in 12, there were just fewer functions that started with decode, so it didn't quite work out. So then I started looking at iMessage. iMessage is the default messenger on the iPhone. It can send messages to both Macs and iPhones, and it's an encrypted peer-to-peer messaging format. It has many, many formatting features. I mentioned extensions. There's other things like you can send bold text, that sort of thing. And I worked with Samuel Gross on this part of the project. So to start off, Samuel Gross wrote an iMessage sending and intercepting client. It was pretty cool. So basically, it just used Frida to hook specifically the dictionary being encoded or decoded, and then you could see the incoming and outgoing messages. And it works on a Mac or an iPhone. It's a little bit more work. So I guess for sending, you always want to send from a Mac. There's no good reason to send from an iPhone, but sometimes you want to see the message received by the iPhone. And that was a little bit of work to set up, but we ended up getting it working on both. So this is what an iMessage looked like. And you can see it has some interesting fields. There's like the P equals, and that's who you're sending it to. There's the text, which is hello black hat, a few other things, the version. And here's what we think kind of the interesting fields were. I mentioned the text, and then there's this plugin stuff. So there's the balloon identifier. which is kind of like a MIME type for iMessage. It'll say like, oh, this is a talking giraffe, or this is handwriting, or that sort of thing. And then the BP is the plugin data, and that is the data that's interpreted based on this balloon identifier. And then there's kind of two more interesting ones. There's the participants, which is where it goes. And then there's the attribution info. And this is basically related to attachments, where they're from. So we started to look at iMessage serialization because we noticed that these two fields, BP and ATI, were serialized using NSKeyed archiver serialization. And basically, this is a format which is a plist, which is basically an XML format. And in this XML format, it contains classes, and then it will call on the classes a method called initWithCoder to actually instantiate the class. And there have been some past bugs in initWithCoders, including a few that allowed local privilege escalation found by Ian Beer. And here's an example of something serialized with NSKeyed archiver serialization. Starting on the left, you can see that there's the class. So this is an NSURL. You can see the class hierarchy. And what'll happen is when this is decoded, this object on the right will reference that class, and then it will call initWithCoder, and then initWithCoder will decode these two fields, the ns.base and the ns.relative. And then you can see the base is 6, which actually references this string, natashenka.ca. So this format will be deserialized into an NSURL object in that way. So serialization has a few security features. One of them is NS secure coding, and this is basically two features. One is that it requires that when a class creates an initWithCoder, they also have to create another method, and this method cannot be inherited. It has to be created directly. And basically, this just means that you cannot create an initWithCoder by mistake. If you're a developer, you have to have exposed it on purpose. The other thing is that it requires a list of allowed classes to be provided when you're deserializing. So if you're, say, deserializing that URL, you have to say, I want to deserialize a URL, or I want to deserialize a URL or a dictionary. But you can't just leave it blank. You have to limit it in some sort of way. Unfortunately, this NS secure coding is not enabled by default. In fact, there's what I call safe and unsafe initialization methods for NSKeyed and archivers. And you can see there's the safe ones at the top and the unsafe ones at the bottom. And there's especially this one. I mean, could anyone ever forget which one of these is safe and which one of these is unsafe? So we thought that it might be a good idea to see if anyone accidentally did decoding insecurely. There are a few places, as I mentioned, where deserialization happens. There's this BP in Springboard, which is the user interface for the iPhone. And this will basically first decode this BP, and then if it's an extension, it will also call this method preview text on it, which in practice is only used if a link is being sent. And this turned out, in my opinion, to kind of be the best attack surface because it had the largest array of classes it would decode, and also it has a very high privilege level. It runs as mobile, and it has no sandbox. And then there's also mobile SMS, which is the actual SMS app, which also decodes this with one click. And then there's ATI, which is an IM agent, and this one has kind of a smaller attack surface because it doesn't decode as many classes. So our first idea was, let's find an insecure deserialization call, and then let's create a WebKit instance. And then exploitation will be solved because there's a lot of WebKit vulnerabilities, and there's a lot of known exploitation methods, and maybe we could get an exploit to work this way. And yeah, we looked at Springboard and we looked at IM Agent, and yeah, we did not find any insecure calls, even though the API was a little bit confusing. So then we decided, let's look at these extensions. You know, there were quite a few of them, and some of them looked new, so it seemed like a good attack surface. And we hoped that maybe they would misuse a deserialized object. And I found this vulnerability, which is not a very good quality bug. Pretty much this extension would decode a byte array, and it would also decode a length of the byte array, and then it would read out of bounds. It would trust the length of the byte array, even though the byte array that's actually deserialized could have a different length. I don't think this is a very exploitable bug, but I thought it was kind of interesting in the first place that you could have a bug like this remotely. So we looked even more. One thing that we looked at a lot was this link presentation layer. So the link presentation is if you send someone a link, they'll get a preview of the link, they'll get an image, maybe a preview of the text. And I think this actually has fairly good design in that the person who sends the link takes all the risk. It is loaded on their device, processed with WebKit on their device, and then only the results, the image, the text, is sent to the other device. So we were hoping that maybe we could find a way to trick this to make it so that maybe the link gets loaded on the receiving device, and then that's a WebKit instance that could be exploitable. But we looked and looked and didn't find anything like this. So then the other idea was to see if we could find a bug in the supported deserialization code. So we went through all the available initwithcoder implementations. And there were a lot. So thinking about this BP field that gets decoded in Springboard, this is the list of allowed classes. I won't read them all, but it's like NS Dictionary, NS String, and a lot of other things. They do have to support secure coding, but most things that inherit from these classes do anyhow because they're meant for some type of use by a different process. But what's also interesting is that the subclasses were allowed too. And the subclasses come from every library that is loaded into Springboard. Even if it's not intended for serialization, every one of these subclasses that allow serialization that gets loaded is allowed. And this wasn't the entire DLLD shared cache. It does actually have to be DL opened or explicitly imported, but it was still quite a large attack surface. So we looked at these, and I found this vulnerability, which is also a little bit unusual. The problem is that it allows a subclass of NS data that is file-backed. So that means that you load the NS data, and then you have a file location, and then when you use the NS data, that file is the data in the NS data. And this kind of had two problems. One was that it trusted the deserialization length, even though the file could be shorter. So let's say you had like a 10-byte file, and you said it was 20 bytes long. The rest of that would just be uninitialized memory. But then there was another problem, which turned out to be a bit more serious, which is that that's supposed to be a local file. But the check for that turned out to be faulty. So you could fetch this from a URL, which made this bug have a very interesting effect, which is that you can retrieve a file from an iPhone remotely without any user interaction. The way this works is that you create the NS data with the file, and then you convert it to the NSURL. And this was a very long process, so I'm going to gloss over it a bit. But basically, there were enough objects you could deserialize so that you could encode it, and you could make it a URL. Then you would use this bug again and visit the URL, because you're allowed to visit a remote URL. And then this would just send you whatever file, for example, the SMS database you were pointing to. Though it did have a size limitation, about 40 kilobytes. So we're thinking about this and this very interesting bug, and then Samuel had this idea. What happens if a class does not have an initwithcoder, and you try to instantiate it? And the answer, weirdly, is regular inheritance rules apply. So let's say initwithcoder calls initwithcapacity, and you're a subclass. It will call the subclass's initwithcapacity, and so on for lots of different methods. And there were a few inheritance checks. So some instantiations, they would say like, oh, this has to be inherited directly, but not always. So we found this vulnerability, which is basically, there's this class, PF array, that had initwithObjects count defined, and this is called by array initwithcoder. But unfortunately, this array class, I'm assuming everything that's in it already has a reference, because it doesn't keep a reference to things that are in the array. So if you create this array and then you drop all the references to the objects in the array, those objects just get freed. So that was a very interesting bug. But then, it gets even more complicated than that. So remember the plist I showed you, where there is the numeric reference to the object, the string? What if there's a cycle? What if, an object points back to itself with the reference? Or what if the object goes through another few objects and then points back to itself? And the answer is it gets complicated. So how does the serialization actually work in this context? Well, to start off, let's say you're deserializing NS_SUM class. Well, it will allocate that sum class, and then it will put that in a temporary dictionary, which, by the way, doesn't have any references. It's assuming that the fact that you decoded it means that you already have, or the fact that you allocated it means you already have a reference. Then it calls init with coder, and that happens, and then it will clear the temp dictionary and put it in a permanent dictionary. Now what happens if you decode an object twice? Well, now you have these checks. And what this will do is it will pull it out of the dictionary, then make a copy of it, and then it'll also check the permanent dictionary and then go through the init with coder. So this has some interesting problems. One is that the object can be used before the init with coder is complete, which isn't great. That might violate some assumptions. But then there's this other problem, which is, if you look at, in the documentation, what an init function is supposed to do, it is not guaranteed to return the object created by alloc. It can actually free that object and return its own object if it wants. And this temporary dictionary has no references, so you could free the last reference in your init and then use the thing from the temp dict, and it would not have any references to it. And I actually never found any bugs using the second problem, but I just found it interesting because it's something that I think is problematic with the design that could cause a bug. But what all the bugs ended up being in is this cycle problem where the init with coder is not complete. And unfortunately, this vulnerability was not remediated properly in the fix, so I have removed the class. But basically, the idea is there is a class that when you decode it, it creates a single list length of things. And then it will, based on that list of things, create a buffer. And then it will put things from the linked list into the buffer. And if you can cycle in this, you can end up in a situation where the buffer is too small. The linked list is calculated, its length is calculated, the buffer is allocated, and it's actually not done completing that list. So this ends up being an out-of-bounds read, which you can call a lot of methods on, and it's kind of an interesting bug. And so this has a lot of stuff missing, but this is mostly just, if you've ever wondered, how do I POC this stuff? The answer is, I look like a crazy person drawing these diagrams all day, and it took about 8 hours to make this diagram with the pointer bad into an actual object that caused a crash. So there was another bug that involved cycles as well. And this was in a dictionary called NS Known Key Dictionary 1. And this is a dictionary where you have to declare the keys up front, and you'll get a lot of optimization in return for that. And basically this, you would provide an array of key data, and you would also provide a length. And the length would eventually be checked to be consistent with the key data. But it didn't happen soon enough. So you would have the length, and then you would be decoding the key, and then you could end up using this class before it was done, and then that length won't be checked yet. And this ended up being a memory corruption vulnerability where it would go out of bounds before it hit this length check. So that was actually interesting. So one question you might have would be, why are there so many bugs in this NS Keyed Archiver? I think I showed you 3, but we reported about 8 at this point. And it seems to be one of the buggiest interfaces in the remote attack surface, and here's why. Let's say you have a URL and you want to decode a URL. And one thing that's already surprising is the attack surface of that depends a lot on how you compile it. It depends specifically on what frameworks you include while you're compiling it. But let's say you do this with just one framework, which is user notifications. Then what's your attack surface? Well, you have the NSURL init with coder, which makes sense. And then let's say in your class, you create a URL subclass. Then that init with coder is in the attack surface too. And then you have any subclass of URL, which is in all the frameworks you included. And I just included this one framework, which is UN security scoped URL. But there's more attack surface. So what does NSURL init with coder look like? This is kind of a pseudocode dramatization of this URL with a few things missing. But what's important is one thing it will try to do is decode an NS data. And if that's the case, it will try and treat that like a bookmark. And this is actually a whole second serialization format that it'll try to decode, which is attack surface. And alternately, if that doesn't work out, it will try and decode these strings. And it'll decode the URL base and the URL relative, and then create your NSURL, which is interesting. That means that now you have strings in the attack surface, and now you have data in the attack surface. So now you have all the subclasses of those included in your attack surface. So you have this NS-dispatch data, NS-localized string. I won't read them all out, but everything in, there's two default frameworks which are always included, Core Foundation and Foundation, plus there's this user notifications. And now we have a total of 5 init with coders also included here. And then you got to continue all the way down, right? So, for example, now you have this UN localized string init with coder. This one decodes an NS array. So what are all the subclasses of the NS array? And then this NS localized string decodes dictionary, date, and number. Well, now you need to include all the subclasses of those in your attack surface. Then there's this problem with the subclassing without the init with coder. So for example, the string init with coder we'll call init with string. So now every subclass with an init with string is included, and likewise with the NS data, there's init with bytes. So this increases the attack surface, and keep in mind you also have to do this with like the NS array, the NS dictionary, and also any objects that get decoded when creating those. And what's funny about this is if you're decoding a URL, you probably just want a string, right? 99.9% of the time, no one's actually using this. And this gets even worse. Imagine adding a few extra allowed classes. Let's say you want to decode an array of URLs. Or let's say, you want to import a few more libraries, or like dozens of libraries like Springboard does. And imagine being a developer trying to secure this. My opinion is that securing a class in the face of NS-keyed archiver is an intractable problem. There are just too many interdependencies between unrelated components, and it requires full knowledge of all other components, which might be okay if you're Apple, but if you're, for example, a third-party developer trying to do this, how are you going to know that you got to worry about this being the, UN scoped URL? It also means that small changes to low-risk components have unexpected consequences. My suspicion is that the majority of these bugs did not occur because someone wanted to add this to the attack surface of iMessage. They happened because someone added an init with coder to the calculator, and then they wanted to add 2 numbers in Springboard, and someone imported this library, and no one thought of the fact that these are going to combine in a weird way and cause bugs. So this is a situation where I think this design causes a lot of security problems and is very problematic. So now I'm going to show a few demos here. The first one is of this bug that allows for remote files to be fetched. And unfortunately, this is very low production value. This is me typing with one hand while I hold my phone with the other. But you can see here, I have a message, and the message has an image in it. And then I'm sending an iMessage. And that's kind of how the tool works. You just run it on the command line. And then gotta wait for this message to appear. This is the one that's trying to get the SMS database. It's a little bit slow because unfortunately the way that URL decoding ended up working, you have to send a URL that's equal in size to the data you want to retrieve. So these messages kind of arrive pretty slowly. So I pre-prepared this second message. So what happened is I pulled the location of that image out of the SMS database, and I put in the location here so I didn't have to type with my left hand while holding the camera. But in real life, you would get that from the database and put it in the message. And then I'm sending it again. And then this is going to be the message that gets the image. So once again, got to wait for it to arrive. It's funny, I totally know the message will arrive, but every time I watch this video, I still get a little nervous. So you can see the JPEG header there, and then I pull the file off the server, and unfortunately the encoding you get is kind of complicated and requires quite a bit of decoding, so I just pull it off and then run this Python script to decode it. And then look, it's the same image. So I also have a second demo here, which I have to confess we got working about 2 hours ago, which is an example of an exploit. This exploit uses an unfixed bug, but there's nothing bug-specific about it. I think in particular that it would work with that PF array issue. I think it would work with the other out-of-bounds and memory corruption issues. And right now, this doesn't bypass PAC, but we're working on it. And so the way this works, Samuel wrote it. The idea is that you use IMAgent as a crash oracle to break ASLR. So when you send a message via iMessage, you get a confirmation back. So the idea is if you lay out certain things in memory, sometimes it will crash and sometimes it won't. And based on whether you hear back again, you can basically infer things about how things are laid out in memory. And this has to be IMAgent because Springboard is a very noisy crasher. For a while, it would actually freeze up the device if you crashed it enough, but IMAgent will restart consistently, so that made it better. And then, so the first thing that happens is this bug will break ASLR by using this oracle, and then basically it will use a heap spray to create the fake Objective-C object, and then that will typically call selectors in Objective-C. So here we go. And anyhow, Samuel's demos have way better production value than my demos. So here is the version, and here's showing that nothing's in context. This is someone you have never messaged before. And then this demo shows incoming messages on purpose. This isn't necessary, but it's kind of a boring demo if you're just sitting here. So you'll see messages coming in, and those are the oracle that's bypassing ASLR. And you can see time. Yeah, I'm assuming that actual attackers wouldn't do that, but maybe. So this is also sped up in time, so you can see the time at the top. And this takes, I think, about 6 minutes total. So there we go, and now we're getting ready to pop calc, and so basically what this is doing is that it's trying to lay out the heap, and then it's actually checking the notifications to make sure that things are actually in the right place before it hits the trigger. Yay, there's a calc. So, unfortunately, I think I could probably do a whole other talk about both of those demos. So I haven't included a lot of detail, but we will be blogging about them shortly. So watch our Project Zero blog if you want to know the nitty-gritty of exactly how those two demos worked. So in conclusion, fully remote iPhone bugs do exist. We found about 10 of them, so I think that at least puts to rest the question of, are there really bugs like that? The remote attack surface included a lot of things, including SMS, MMS, VVM, email, and iMessage. And we found bugs in VVM, email, and iMessage, so it's certainly not just an iMessage thing, though the majority of the bugs were there. There were design problems with iMessage serialization that make it especially prone bug surface. And I do want to say that this is also a fairly old attack surface. Serialization was used for other things that weren't iMessage for a long time before iMessage. So this is kind of a difficult problem. How do you cut stuff down? But right now, even with the NSURL coding, there still is a lot of security problems. And it's because of that exploding attack surface. There's just no good way to evaluate or reduce the attack surface of something you're deserializing, even if you are just deserializing one string URL. There are methods for an attacker to send malformed messages in most formats, and we actually released them today. So if you take a look at this URL, we have the iMessage sender, there's the IMAP server, and there's the SMS tools. And I'm hoping that people will use these to look more at iMessage and hopefully report some bugs that we didn't find in this project. And I want to end off by just reiterating that this is an especially dangerous attack surface. It doesn't require proximity to a user. It doesn't require network intercept. These are basically bugs that anyone can use from anywhere to attack anyone. And I think that makes them especially dangerous. So it's important we do what we can to reduce the number of these bugs and make them less available to attackers. Thanks a lot.